Hello बच्चों, सत श्री अकाल and namaste from my side. How are you all? So guys, this is Indrajit Singh welcoming you all into the most sensible platform for an aspirants those who are preparing for JEE NEET kind of examination. So guys, this time we are back. Previously we did rotational motion. It was completely divided into the two parts. First was of the center of mass and the second one was about the remaining part of the rotational motion. Now today we are moving forward to the gravitational part. Yes, the gravitation. Small chapter, simple chapter with the limited number of the theories, an awesome thing. Small chapter, limited chapter. Sorry, small chapter with a limited number of the theories, right? And things are going to be quite awesome. So are you all ready? Yes or no? Come on everyone, those who are watching this lecture. So I'm having in the habit of, right, speaking up on the live, that's why. So guys, yes, gravitation, we are going to move forward. What things we are going to see into the gravitation? What things we are going to see? First of all, the most important thing, that is Newton's law of gravitation. The Newton's law of gravitation and the Coulomb's law of electrostatics, right? The Coulombian force into the electricity, they are right analogous to each other. One is for the two charges, the another one is for the two masses. One we are having the one we are having the gravitational constant, second we are having the permittivity, right, of the specific medium, and the relative one. Okay, there is a slight difference between two. Analogy to both, like analogous to the electrostatic force, right? The Coulombian force is not analogous to the Coulombian force into an electrostatics. Okay, it's like attractive and repulsive in nature, but here the gravitational force is only attractive in nature. Gravitational force is only attractive in nature. From gravitational force, we are going to define what will be the value of G at the surface of the earth. How the value of the G varies while moving on to the height, how value of the G varies while moving on to the depth, how value of the G varies from pole to equator, altitude, latitude, height, or in another sense it's altitude only, and depth. Then we will see a bit concept of the gravitational potential. That this thing entirely will be compared, right? It will be combined into the work energy theorem. Yes, work energy theorem, right? I told you all while dealing with that part into the 6th chapter, right, that this holds a prominent position into the physics 11-12 syllabus. The reason behind it is, okay, the reason behind it is it is going to use into the gravitation. We are going to use that into the rotation. After that, it will be completely used into the solids, fluids, electrostatics, SHM, waves, capacitor, into the different forms. Energy forms are different, but everywhere work is going to be done, and this work energy theorem is going to come. If we are dealing with the heat and thermodynamics, then this will come into the form of heat energy, right? Okay. If we are dealing with into the electrostatic, then it is going to come into the electrostatic, right, potential, energy, and the respective work done. Okay, if we are going to deal with the respective capacitance, then whatever the amount of the energy that is stored into the form, into the electric field inside the capacitor, it is going to come into that form. So everywhere work done is going to happen. Okay, and lastly we are going to discuss rapidly the Kepler's law. Okay, so I think, shall we begin? Yes or no? So we are going to move forward to the Newton's law of gravitation. What does it states? Right, the Newton's law of gravitation states that, first of all, two masses, okay, rather than to move on to that, every mass in universe has tendency to attract another mass. Every mass into the universe has a tendency to attract the another mass, right? This tendency of the attraction, okay, in another sense, this tendency, see, simply being a teenager, you can understand the meaning of the attraction. Okay, being a teenager, you can easily understand the meaning of the attraction. मैं तो रास्ते से जा रहा था, भेलपूरी खा रहा था, नजर हटी, दुर्घटना घटी, तो मैं क्या करूं? रास्ते से जा रहा था, भेलपूरी खा रहा था, नजर हटी, दुर्घटना घटी, मैं क्या करूं? So here what the attraction, the law of attraction acts, right? Well, some of the studious people, for some of the studious, right, the most concentrate, like students, those are having the high amount of the concentration and the focus on the studies, they might have read the all of the law on the basis of law of attraction by, okay, Sir Brian. Okay, so for them attraction is something else, the help from the nature. Okay. So in the entire universe, each and every mass is having the tendency to attract the another mass. Okay. Now that tendency is gravitation. And that tendency acts. If I want to suppose, let us take an example, if I want to represent any physical quantity, that any activity that is going on, then obviously physical quantities are needed. If I want to represent anything, okay, obviously then the physical, this quantities are needed. So this tendency to attract the another particle, even at being at the infinite distance, tendency to attract the another particle, even being at the infinite distance, then what is going to happen? Okay, it should be in terms of some physical quantity, it should be defined in terms of physical quantity, right? Okay. So that is nothing else but a gravitational force. Suppose this is mass m1, this is mass m2. m1 and m2 are the separated by the distance r. The tendency of m1 is right to attract m2. The same tendency m2 has towards attracting m1. Because according to the Newton's third law of motion, forces always occurs in pair. Forces always occurs in pair. M1 has the tendency, simple, if, right, M1 has the tendency to attract the another particle, the same tendency of attraction M2 holds. Same tendency of attraction M2 holds. Okay. Now even if the tendency of the M1 is defined in terms of a physical quantity, that is a gravitational force, the tendency of the M2, okay, is also defined in terms of the force, that is a gravitational force. In another sense, according to the Newton, both forces are equal in magnitude and opposite in direction. Okay. So here what does this Newton's law state? Right? It states that if this is two masses, right, are separated by the distance r, right, the force acting between them, the attractive force, right, acting between them, right, is directly proportional to product of the masses and inversely proportional to the square of distance between them. How it derived, how we reached up to the results, how conclusions were defined, right, all of those stuff are still into the journals, right? Okay, but right now, like being a student of 11th and 12th, we are accepting this stuff. Whatever, suppose he is having the tendency to attract this particle, so obviously the force acting on 2 is because of 1. Let's say this is 1 and this is 2. Similarly, he is also having the tendency to attract the 1. So can I say this is force acting on 1 as because of 2? See, they both are into the opposite direction, they are into the equal magnitude, right? So if there occurs a tendency, it is acting in terms of the force, and forces are always into the pair. One is having the equal attraction toward the another, right? Okay, the same applies vice versa. So in that case, if raste se ja raha tha, bhel puri kha raha tha, okay, so here force was not in pair. That's why you met an accident. Force was not in a pair. रास्ते से जा रहा था, भेलपूरी खा रहा था, ठीक है ना, नजर हटी, दुर्घटना घटी, मैं क्या करूं? So here, if the force, the tendency of the attraction you might having, right, towards an X person or Y person, the same tendency the person was not holding for you. She was not having any kind of the emotions for you. So for that reason, according here, the Newton's law of motion was violating, right? Why? The forces were not in pair. If you are having the attraction towards her, she was not having the same attraction, right, towards what we can say on the opposite side. But she was lying onto the some person who is having the six-pack abs rather than to move on for the six-pack, right, money. Okay, so in that case, what happens? Nazar hati, durghatna ghati, main kya karu? Newton's law is getting violated. The disaster thing is going to happen. Okay, so now here, the force acting between them is directly proportional to the masses and inversely proportional to masses and inversely proportional to square of distance. This is a statement of the Newton's law of gravitation, and in which, right, whatever the amount of this force is acting between the two particles, it is known as the gravitational force. There are some noteworthy points, right, okay, regarding this gravitational force, and that we are going to discuss it now. Okay, there are some noteworthy points related to the, right, gravitational force. Okay, now we are going to discuss that part into the detail. Okay, so stay tuned. You are going to enjoy the each and every moment of it. The first part, the gravitational force is always attractive in nature. Gravitational force is always attractive in nature. Always. We are not having any kind of the repulsive gravitational force. Okay. Second, at infinite, right, as F is inversely proportional to R square, at infinite the gravitational force is 0. At infinite, it means that if particles are separated by the infinite distance, if particles are separated by the infinite distance, then obviously the gravitational force between them is going to be 0, right? Okay. Gravitational force between them is obviously going to be 0. Okay. Now what happens here, as F is inversely proportional to R square, lots of, right? Now the third point, this is a scalar form. It can also be described into the vector form. It is not applicable for more than two bodies, right? And the last point, to calculate the gravitational force between the continuous body, right? Okay, the way is different. These are the some noteworthy points related to the gravitational force. Okay, some noteworthy points related to the gravitational force. First, the gravitational force is always attractive in nature. As F is inversely proportional to R square, right? Particles are, right, F is inversely proportional to 1 by R square. If the particles are separated by the distance infinity, force is going to be 0. Right. F can also be described, okay, into the vector form. Why? Because in an entire three-dimensional space, right, this position of the two particles are always with respect to the reference point, and it can be any vector into the entire three-dimensional space. So for that reason, this was just an explanation of the, right, the Newton's law into the vector form. If suppose a particle is having the position at any point into the three-dimensional space, then that position is described with respect to origin, right, with the vector. So for that reason, the Newton's law is also described into the vector form. Let's have another thing to discuss. F is inversely proportional to m1 m2 whole divided by r square. Removing this proportionality sign, we are going to get F is equal to G m1 m2 whole divided by r square, right? F is equal to G m1 m2 whole divided by r square. Okay, so here what is going to happen? What is this G? This G is nothing else but an gravitational constant. The value of the gravitational constant was defined, right, as G is equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square, right? Okay, Newton meter square per kg square. Yes or no, guys? Okay, now here there is an important thing regarding, okay, how the Newton's law of how this gravitational force is affected by multiple factors, right? Okay, how this gravitational force is, right, okay, affected by the multiple factors in terms of, suppose, let's have the strict comparison on which the maximum number of the questions are going to come up into an examination. The very strict, first, the gravitational force depends on the distance between the masses. Second, gravitational force completely depends on the density, right? It does not depends on the medium. So first of all, let's have the strict comparison. Suppose this is of mass m1 and this is of mass m2 and they are separated by the distance r. One is of mass m1, second is of mass m2. Hope so they are separated by the distance r. Okay, so the gravitational force acting between them is defined as G m1 m2 whole divided by r square. G m1 m2 whole divided by r square, right? So in this case, what? Suppose this entire thing is immersed into the liquid. Right? They are separated by the distance r and this thing is completely liquid, right? Immersed into the, right, liquid. Okay. Then the gravitational force into the medium is going to be same. F is equal to G m1 m2 whole divided by r square. Okay. The gravitational force is affected by the medium, right? The gravitational force is not affected by the medium. Apart from this, the most important statement is F depends on distance r and F varies with density. Okay, slowly we are going to see its vector form. We are going to see the superposition principle. Okay, lots of things we are going to see. Okay, we are going to overcome the one of the most important limitations of the, right, Newton's law, that it does not depends on the for more than, if there are more than two particles, right, then Newton's law fails in spite of being the universal law of gravitation. Actually, it's not Newton's law of gravitation, it is universal law of gravitation. It is accepted universally, despite of being like the values are getting changed, the values differs, right, at each and every point into the universe depending on the what planet you are talking about. But the thing is, it differs, right? It is the universal law of gravitation and it is accepted universally. Now some students might be thinking, sir, which alien organization or which alien, right, the civilization is going to come and accept this thing universally? You are saying universally. At least it is accepted universally and it is has crossed through, right, thousands of tests and still the, right, the researchers are having research on it. Okay, but it is universally accepted because value of the G and gravitational forces everywhere, just the value differs. Okay, so now the classification of the law of gravitation. Okay, the first, Okay, it is defined into the scalar form and vector form. It is defined, okay, superposition principle is there for more than two particles, right? It is even into the scalar form, right, into the vector form. Okay, same for more than two particles. This is an example of the superposition principle. If you want to calculate, right, the resultant force of the earth as because of the rest of the planets on the solar system, then obviously the superposition principle is indeed needed. Okay, the superposition principle is indeed needed. Anyhow, it is needed. Okay, now what is going to happen here? If suppose particle is right at any position into the three-dimensional space, is it for sure that Indrajit sir is going to stand onto the x-axis at the origin and else is going to stand at x is equal to 2 and we are going to calculate the gravitational force? What about Indrajit sir is at somewhere else place and you are at some else place, right? Then what is the actual tendency of the attraction that you are going to show towards you us all, right? What is the actual tendency of attraction that you are going to show towards us? Okay, that tendency of the attraction, right, into the for the particle towards another at any position into the three-dimensional space, at any position into the three-dimensional space, then what happens here? Okay, suppose this is a particle of mass m1, this is a particle of mass m2, this is a position vector r1 and this is a position vector r2. These positions are defined with respect to the reference point and that reference point is nothing else but an origin. The same law can be defined into the vector form. How? Force acting on 1 is because of 2 is directly proportional to G m1 m2 whole divided by r1 minus r2 whole square. But as this is into the vector form, so for that one unit vector is always added. Okay, unit vector is always added. Okay, unit vector is always added. So here what is going to happen? Just hold on, guys. Unit vector, according to the definition of the unit vector is defined as a vector by its magnitude. So further, if we are elaborating this part, then we are going to get it as f12 that is equal to G m1 m2 whole divided by r of 1 minus r of 2 whole square, right, into r of 1 minus r of 2. Right, r of 1 minus r of 2. Okay, here at the bottom we are going to have the cube. Into the bottom we are going to have the cube. Okay, so this is the form of the gravitation. Now see, this is mass m1, this is mass m2. As I said you all, this is number 1, this is number 2. 1 is having the tendency to attract 2. So the force acting on, right, 2 as because of 1 is will be in this direction. Similarly, we are talking about the tendency of the 2. Tendency of the 2 to attract the 1. Obviously, the force will be in this direction. So here, okay, this will be force acting on 1 as because of 2. They are opposite into the direction and equal into the magnitude. So how we are going to define that part? F1 of 2 that is equal to negative of f of 2 of 1. F1 of 2 that is equivalent to negative of f2 of 1. Right? Negative of f2 of 1. So this is all about the vector form. Okay, this is all about the vector form. Now further, if we are moving on to the limitations as I discussed, and we are going to overcome that part, it is only applicable, right, it is only applicable for the particles it is only applicable for the system of the two particles. If more than two particles are included into the system, the Newton's law of motion fails. Sorry, Newton's law of gravitation fails. Okay. Second, in a universe, all of those objects, right, with are not the they are not an absolute particle. We can't say that. Okay, none of them, right? Some might be having the point masses, but I can't say, right, that every particle is of the point mass. So here exists the concept of the rigid bodies. Okay, here exists the concept of the rigid bodies. How the calculating the gravitational force between the bodies with the masses and densities, or in another sense, bodies with densities and point masses is different. And point masses is different. So these are the two limitations that we are really going to overcome. The two limitations that we are really going to overcome, and we are going to see that part. How? The first limitation. Suppose if the system is having more than one particle, what is going to happen? Suppose system is having M1, right, M2, M3, M4. The Newton's law of gravitation, it is only valid between the two particles. Either it can be into the pair of M1, M2, it can be into the pair of M1, M3, it can be into the pair of M1, M4. Lots of things are there into the pair. Okay, it can be into the any pair, but here what happens? Right, it can be into the any pair, but here what happens? The thing is, okay, if you want to calculate the interacting force for all of those particles, it is not possible according to the Newton's law of gravitation, the limitations of it. Okay, it is not possible to calculate the all of those forces, right? Okay, so in this case, what is going to happen? Okay, the superposition principle we are going to use. What does it states? It is impossible to calculate interacting force between multiple particles. It is impossible to calculate, right? Okay, it is impossible to calculate the interactive force, but it is possible. Okay, sorry, I'm going to write it down here. Okay, else. Okay. It is possible to calculate the resultant force on one particle as because of others. Right? It is possible to calculate. Yes, it is possible to calculate. It is impossible to calculate the interacting particles if more than two are present into the system. It will violate the Newton's law of gravitation. But it is possible to calculate the resultant force on any one of them that is acting as because of the n number of the particles that are present into the system. How? Suppose this is a first particle, this is a second particle, this is a third particle, dot, 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 this is an nth particle. The step one is select the reference particle on which, right, you want to calculate the force. Select the reference particle on which force needs to be calculated the reference particle, suppose if we are selecting the reference particle as the one on which we need to calculate the resultant force, okay, then that equation is defined as this is the resultant force on 1. The force between 1 and 2, force acting on 2 is because of 1. Force acting on 3 is because of 1. Right? Because he is having the tendency to attract. Na? Force acting on the nth particle is because of the 1. Right? Or you can even write into the reverse form. Okay, how? See, F acting on 1 and 2. So that is F acting on 1 on 1, F acting on 1 on 2, right? Plus F acting on 1 on 3, plus F acting on 1 on 4, plus dot 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 dot, right? F acting on 1 of n. F, the force on of the particle with respect to the same one, it is going to be 0. So according to the superposition principle, F, the resultant force on the 1, it is F12, F13, F14 plus dot 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 plus F1 of n, right? This is what the superposition principle is all about. Select one reference point, okay, apply Newton's law of gravitation, right, individually. Okay, this is right how the superposition principle is defined. Okay, this is how the superposition principle is defined. Okay, now what happens here? Superposition principle. Okay, superposition principle. Are all of those particles only located into the 1D or no? The n number of the particles right are located at any point into the three-dimensional space, right? So for that reason, the superposition principle is described into the vector form. As of that reason, the superposition principle is derived into the vector form. Now, how we are going to define this stuff? Suppose this is particle 1 having position vector r1. This is particle 2 having position vector r2. Right? This is particle 3 having position vector r3. All of those position vectors are with respect to origin. Step 1. Select the reference point F1 into the vector form. Force acting on 1 as because of 2 plus force acting on 1 as because of 3. Here another fourth particle is also there, right? Okay, with the position vector r of 4, and this is fourth one, right? So here plus force acting on 1 as because of 4. Now let's calculate how this force is acting. This is a 3, this is right. 1 is having the tendency. See, 2 and 1, F2, force in between 1 and 2. Force as because of 4, force as because of 3. The resultant, the vector addition of all these forces will give the resultant force on the first particle. The vector resultant of all forces, right, is going to give so suppose if we want to elaborate this expression, okay, if we want to elaborate this expression, then it is going to be like f of 1, that is equal to g m1 m2 whole divided by r1 minus r2 whole cube r1 minus r2 into the vector form, plus g m1 m3 whole divided by r1 minus r3 whole cube, and that is r1 minus r3. Similarly, plus in between the gravitational force between, right? Yes, this is the longest calculation. The calculation base sums into the Newton's law of gravitation, right? The longest calculation based sum, right, into the Newton's law of gravitation. Yes or no? G, M1, M2, this is how they superpose. So till now we have discussed the four most important parts, right? Okay, till now we have discussed the four most important parts, right? The Newton's law of gravitation into the scalar and vector form, okay? The superposition principle into the scalar and vector form, and second limitation is given into the sum of the resources. Second limitation, to overcome the second limitation, to calculate the gravitational force between the rigid body or in the continuous body with the densities and the another point mass, okay, it is given into the sum of the resources, and in maximum number of the resources, direct sums on the basis of it are given. Direct sums on the basis of it are given. Okay, so here what we are going to do, okay, what we are going to do now, directly we are going to move on for the sums basis on it. Okay, two astronauts are floating into the gravitational free space after having lost in contact with the spaceship. The two will what? Two astronauts are floating into the gravitational free space. This question is asked in NEET 2017. They are keep floating at the same distance. They will be right, okay, they will become stationary. Will they move right towards each other? Okay, suppose let us take an example. This is right at the astronaut 1, right, and this is at the astronaut 2. Obviously they are going to separate it from the spaceship, so the distance become going to be quite large. Large doesn't mean infinity. As the distance is going to be large, the value is going to be nearer to 0, not exactly equivalent to 0. From theory point of view, we are taking it as nearly equivalent to 0 and we are considering as the infinite point. But in entire universe, the practical approach loudly speaks that exactly we are not able to define the infinity. Exactly we are not able to define that this is the boundary up to which the gravitational field of the earth is acting. This is the boundary up to which this thing is acting. This is the boundary up to which this thing is happening. We are not exactly able to define that part. So what happens, right, in spite of being right at the large distances, they are going to right attract, they should have the tendency to attract each other, right? So it is not for sure that they are going to float at the same distance, they will become stationary, they will move. Obviously, as because of the attractive nature and because of the Newton's law of gravitation, okay, with the very least speed, I must say, but obviously they are going to move, right, as because of the mutual law, right, force of the attraction, they are going to move right towards each other, and this is the perfect answer for this specific question. Okay, now let's move on to the next question. Two particles of equal masses m go around a circle of radius r. Two equal particles are there of masses m. They go around a circle of the radius r under the action of the mutual force of attraction. The speed v of each particle is defined as. First of all, it is important to define the situation, right? This is m1, this is m2. Both are identical, so masses are m. They are separated by the distance of r. Now they are moving around a circle as being right of the identical masses, right? Both might be having the same velocity vector, right? And the circular path would be like this way, right? The circular path would be like this way. Okay. If they are moving onto the circular path, then there is a presence of the centripetal force. Centripetal force, if centripetal force is present, then who is going to provide that? See how we are linking up the data that is given into the question, and slowly we are reaching up to the solutions, right, and up to the final answers. And it is mentioned that the data is given they're moving onto the circular path. Yeah, this is true. If they are moving onto the circular path, then the centripetal force is responsible behind it. If centripetal is there, then I should think that who is going to provide the centripetal? So obviously, whatever the mutual force of attraction that is acting right in between the two particles, the gravitational force that is acting between the two particles is going to provide the necessary centripetal, right? Okay. The gravitational force is going, now see, both are having the identical masses, right? So they are going to move with the same velocity, right? Magnitude, okay, they are going to move with the same velocity. So here the gravitational force acting between them, that is equivalent to mv square by r1. What is the radius of the first particle? R by 2. What is the radius of second particle? R by 2. They are moving with respect to the center of mass. Okay, they always move onto the circular path with respect to the centers, the center of masses, right? Because for here we are in the system, the two particles are included. Na? If system is having more than one particle, then always the center of mass is considered as a reference point, and the right with respect to that part, everything is going on. They are moving right onto the circular path. COM, the center of mass. So for the first particle, the gravitational force is G m1 m2 whole divided by r square. So that is m1 v1 square by r1 that is r by 2. Okay, r by 2. So what it is going to happen, right? What it is going to happen, 1m is going to get cancelled. So it is Gm of 2 whole divided by r, and that is equal to 2v1 square whole divided by r. Okay, Gm1 m2 whole divided by r square, the gravitational force acting between them. Okay, the gravitational force acting between them, okay, of the, okay, actually they are into the circle of the radius r. Okay, I'm sorry. Okay, they are into the circle of the radius r. So here, okay, 2r will be there. Okay, I'm sorry for this. Okay, again we are going to rewrite that part. Okay, the circle is of the radius r. It means the distance between them is going to be 2r. So G m1 m2 whole divided by 4r square is equal to m, right, 1 of v square whole divided by r. 1r is going to get cancelled. The common velocity it is going to come upon as 1 by 2 under root of Gm by r. 1 by 2 under root of, this is a common velocity, being an identical particles, they both will be have the common velocity, and A will be the perfect answer for this specific question. A will be the perfect answer for this specific question. Now this thing can be elaborated. Okay, this thing really can be elaborated into the different parts. Okay, okay, see how it can be elaborated. Okay, let's see. Suppose if not 2, 3 particles are there. M, M, M. Separated by distance R, R, R. If 3 of the identical masses are going to cover up, they are moving around the circle. 3 of the identical particles are moving around the circle, then what is going to happen? The circle would be like this way. If they are moving onto the circle, then obviously there is a presence of the centripetal force. Who is going to provide this necessary centripetal force? The net force acting on each particle. The net force that is acting on each particle is, right, will provide the necessary centripetal force. It means suppose if I'm taking this is 1, this is 2 and this is 3, right? This is force acting on 1, right? Okay. This is force F. Okay, as they are separated by this same distances, let's not move on to the notations, right? This is F, this is F. They are inclined at the 60 degree. Okay, so whatever the net force is there, it is going to provide the necessary centripetal acceleration. Okay, and particles are going to move with respect to the centroid. Particles will move with respect to centroid. Right. Particles will move with respect to centroid. So first of all, let's calculate the net force between, okay, on any reference particle, you can say as 3 of these particles of the identical are identical. So they are moving with the same velocity. Let's say they are moving with this velocity. Okay, actually the vector we are not able to define, but it's just for an explanation. So this is F, this is F. They are separated by the 60 degrees. So what is the net force? Right, so that is equal to F square plus 2F square cos of 60. So the net force, it is going to be under root of 3F. So this is going to be root 3 gm1, or you can say gm square, right, whole divided by r square. This is a net force. The same net force, it is going to provide the necessary centripetal. Now, what will be the radius of the circular path? That is the distance between the vertex and the centroid. In the triangle, the distance between the vertex and the centroid, that is r by root 3. This is going to be the radius for the each particle. So here mv square by radius, that is equal to root 3 gm square by r square. 1m is going to get cancelled, so v square r by root 3 is equal to root 3 gm by r square. So finally the velocity of the each particle, it is going to come upon as v is equal to under root of gm whole divided by r. This is how the Newton's law of gravitation, right, is defined for more than one particles. Now again I am going to give you all one homework part. Suppose if on the 4 vertices of this square, 4 identical particles are there. What will be the velocity of each particle? First of all, we saw things for 2. Second, we saw things for 3. Now this is one homework from my side. Okay, that we are going to see. We have seen the sum, right, for the 4 particles. Okay, for the 4 particles. Okay, now let's move forward. Okay, you can just answer all of those stuff beneath the video. Okay, now let's move on to the next part. Okay, that is variation into the G. Now, what the gravitational acceleration is, how to calculate the right value of it. Suppose you can see this visualization, right? Suppose, let us take an example. Like surface we are talking about, right? We are talking about a surface. Suppose if I kept right, this is a right, the center of the earth. Let us take an example. It is a O, right? Okay, see, we saw the 2 limitations of the Newton's law of gravitation. Okay, first, right, it was completely about this one, right, or it was, yes, to overcome the first right limitations of the Newton's law, right, we use that superposition principle. Now this is important, right? Integration and concept of the gravitational field, what actual the gravitational field is, right? How using this integration we are able to calculate the force between them, between the one rigid body. Let's take an example for this.
always we are considering the earth as the spherical part. Suppose this is the earth, the one astronomical object. This is also the moon, right? Sphere. Both are sphere. They are separated by the distance r. How to calculate? Right, these two are not particles. If distance, right, between two particles, it is very large as compared to the dimensions. If distance between the two particles is very large, right, as compared to the respective dimensions, then and then these two are considered as the particle. But right, okay, this r, whatever the value of r is not as much as, it is not reaching up to that infinite, so we can consider both as a particle, right? So these are the sphere, right? So for this kind of the rigid bodies, right, there is a different way for calculating the force, right? As they are separated, okay, so distance between the centers is calculated, is considered, sorry, not calculated, it is considered. Distance between their centers, O dash, right? Okay, the force always acts on the line joining between the two centers. Line joining the centers. Suppose if two particles are like this way, the force always acts right to the line joining the two centers. This will be the attractive force F and this will be the attractive force F. Right? As this is one of the limitations of the Newton's law. See, suppose if they are separated by the distance apart, we can directly use to calculate, right? We can directly use this formula F is equal to, right, G m1 m2, right, okay, whole divided by r square. But for that, right, we need to have some precautions, like distance between the centers are calculated, are always considered, and second, the force is always acting the line joining, on the line joining between the two centers. Right, if for the spherical bodies separated by the distance apart, if we are using this formula, then these two things are needed to be considered. Now, what about this is an earth. Suppose if object is kept here, right, this is mass m, right. How? For this kind of the configuration, how we are able to calculate, right? For this complex things, right, the integration is needed, right? For this kind of things, right, using this two stuff, we can directly use this formula, right? Slowly and slowly we are going to clear up this concepts, right? And we are going into the deeper, right, of it. Okay, now, see, so this were the limitation, right? So this is for the spherical objects, right? And the gravitational field nearby it, right? Suppose it is a kind of a, see, lots of things or lots of kinds of the objects are there, but spatially we are dealing with the sphere, because all of those astronomical objects, theoretically we are considering it as a sphere, right? So now, suppose, right, we are moving for how to calculate the value of the G. One object is kept at the surface of the earth. Obviously, its weight is acting downward. Suppose, right, the particle is in equilibrium at the surface. Particle is in equilibrium at the surface. Particle is in equilibrium at the surface. It means its weight is balanced by some force, that is the gravitational force, right? Okay, it is not like this way, right? Okay, if the particle is in equilibrium, right, its weight is balanced by, right, weight is balanced by the gravitational force acting between earth and that particle.
Earth and that particle, right? It's sorry, not upward direction, right?
So here, what is the weight mg? Right, okay. What is the force acting? That is g small m, mass of earth, whole divided by distance between the right particle and the earth, and obviously, right, it is r. Okay, the small m is getting cancelled. We are getting the small value of the g as g capital mass of earth whole divided by radius of the earth. This is the value of the gravitational acceleration. This is the value of the gravitational acceleration right at the surface. This is the value of the gravitational acceleration at the surface. But what actually this g means, at the surface particle is at equilibrium, its weight is balanced by, right, its weight is balanced by some attractive force that is acting between the earth and this particle. Right, its weight is balanced by the, right, the attractive forces acting, attractive force between the earth and that particle. Suppose if it is released, obviously according to the Galileo, it is going to accelerate downward towards the earth with the constant acceleration g. The g that we have seen into the third chapter, motion in 1D, motion under gravity, the same g I am talking about. Initially, the particle is at the equilibrium. Its weight is balanced by the gravitational force acting between the particle and the earth. Suppose if it is released, obviously it is going to accelerate downward. Yes. With what acceleration? With the constant acceleration g that is going to, right, fall. Right. And that will be g, this way. So at surface, we are having the value of the g as g capital M E whole divided by R E square. In third chapter, right, in spite of having the free fall, we were not considering any variations in g. But actually this value of g gets changed. See, this value of g is directly proportional to mass of earth and it is inversely proportional to r. If r is getting changed, g will get changed. If mass is getting changed of earth, g will get changed. Right. So this is an important surface, right? Sorry, it is an important stuff. How the value of the g is getting changed, right? Suppose let us take an example. This is at the surface I am talking about. If the particle is raised to some height h, are we having the same value of the g that we are having at the surface? No. Because distance with the respect to the center of the earth increases, g will decrease as because of the inverse relation. Suppose of any situation, this is not a earth, some else planet whose mass differs as compared to earth. Then at the surface we are going to have the same value of the g? No. Suppose let us take an example, this mass is released from the top, right, and it is reaching some at depth d, right, with respect to the surface of the earth. Then also we are going to have the same value of the g? No, things will get differ. Why? Here the distance is getting decreased, obviously g value will increase. It is for sure. See, we are not having the large variations in g, no, right? Okay, and there is a graph also for that, but it's okay. Variations in g are measurable with respect to surface, right? So it means, right, in third chapter we were considering all of those things as a particle, right? At that time we were not dealing with, right, the earth part, right, the earth factors. At that time we were not dealing with the force, right? So in kinematics we were not interested into the cause of motion, that is force. That's why we are considering, yeah, everything the g as constant, yes, it is 9.8. To ease those calculations we were taking it as a 10. But now we are dealing with the force, right? It means whenever we are dealing with this kind of this stuff, so whatever the variations in g are measured, they need to be considered. Whatever the changes are there, we need to consider all of those factors.
classification. How G varies? First, with respect to surface or with respect to C. G varies with respect to mass and densities of the planet. G variation with respect to height from the surface of the earth, right? G with respect to the depth with respect to surface of the earth. These are the three factors with respect to which the value of the G is getting changed. This is only the reference thing. Whatever this formula we are getting, now we evaluated using the example of Earth, as obviously we are living on Earth, that's why. Right? Suppose it would be some else planet with a different mass, with a different radiuses, value is going to be different. I'm talking about the mass, G is different. If I'm talking about the Pluto, G is different. If I'm talking about the Mercury, hell sir, we are not going to stand on the surface of Mercury. I know that. Right? I know that. So you can just understand all of these things, right? You can just understand all of those things. This is a common formula. Kind of variations we are going to have, these things. Let's see this and right. What is the formula of G? First, G with densities. G that is equivalent to capital G mass of Earth whole divided by radius of Earth square. Always, we are always considering Earth as a spherical object. Always consider sphere. It means how much mass that is contained in entire sphere will define its density. Mass contained in entire volume. Suppose this volume of the sphere is given by 4 by 3 pi r e cube. So the mass of Earth, can I say density into 4 by 3 pi r e cube. Can I consider this as equation number 1? Can I consider this as equation number 2? Replacing 2 in 1. Right. We are getting the value of the gravitational acceleration as G. G into density into 4 by 3 pi r e cube whole divided by r e square. This thing is going to cancel, right? Okay. So the small value of the G that is equivalent to, right, G into rho 4 by 3, right, pi, okay, r. 4 G rho pi r by 3. This is what variations of G with respect to densities of the planet. G is directly proportional to rho r. G is directly proportional to rho r. If density of the planet is getting changed, the radius will get changed, G will get changed. Right? Keeping the mass as constant. Right? Everything is between density, mass and radius. See here. Density is equal to mass per radius cube. Right? Directly proportional. Right? Okay. So everything depends. See, if you are keeping mass constant, then obviously density and radius has to change. Right? Okay. To balance this stuff. Right? Density and radius has to change to balance the stuff. It's a very simple thing. Density and radius has to change to balance the stuff. Right? Now, see, it's a very simple thing. G is directly proportional to rho r. G is directly proportional to rho r. Now, let's see what happens. So, this was the first variation, right? Okay. Value of the gravitational acceleration of the Earth, it is G me whole divided by r e square. Another formula we saw, it is 4 by 3 pi rho g r. This is the variation of the G with respect to density. Suppose, as of some reasons, right? As of some reasons, right? Let us take an example of another planet, some X planet, right? For
another planet I'm talking about, right? The value of the g acceleration for its 4 by 3 pi rho g of r, g dash r dash. For this planet, right, the density is twice the density of Earth. For this planet, radius is twice the radius of Earth, right? Then what will be the gravitational acceleration of that planet with the n factor, the gravitational acceleration of the Earth? What will be the value of n? Density is twice. What is the value of the gravitational acceleration of the Earth? 4 by 3 pi rho g r. Gravitational acceleration of the another planet 4 by 3 rho dash g r dash. Right? Let's evaluate this stuff. Right? So it's a g of planet, that is 4 by 3 pi, right, rho dash g r dash. Can I say it as 4 by 3 pi density of planet g radius of planet? So it is 4 by 3 pi. What is the density of planet? Right? It is twice the density of Earth. Right? And g twice the radius of Earth. So g of planet, that is equal to 4 times into 4 by 3 pi rho g r. This will be the gravitational acceleration of the Earth. That is 4 times g. This kind of the questions are always asked in examination. Right? This is a comparison between the Earth and another planet. In some circumstances, right, the value of the density of the Earth is also getting changed. In that case also, we used to, right, we used to evaluate the sum using this formula. With respect to the surface of the Earth, how the value of the g is changing while moving upwards? If I'm talking about the surface, what will be the value of the gravitational acceleration of the Earth? That is g m whole divided by r square. Suppose we are moving at some height. Here. What will be the gravitational acceleration at that height? Can I say it is g of h, that is equal to g of m whole divided by r plus h whole square? Can I consider this as equation number 1? Yes. Can I consider this as equation number 2? Yes. We are going to resolve this thing. What is our motive? Motive to calculate the gravitational acceleration at the height h. And this also we are having two possibilities. What are those? We are going to see. But first of all, let's evaluate the basic formula. So g of h, that is equal to g of m whole divided by, that is r of square, that is 1 plus h by r whole square. Right? Okay. This part is gravitational acceleration as at the surface. Right? So can I rewrite this term as gravitational acceleration at height, that is gravitational acceleration at the surface, into 1 whole divided by 1 by h by r whole square. Right? Okay. This is the actual formula. In another sense, we can also write this statement: gh is equal to g 1 plus h by r. I'm sorry. This is a general formula. Always we have to use this formula only unless and until one special condition is mentioned in the question. All the time we have to use this formula. But suppose if, right, h is less than r, the value of the h is very less as compared, right, to the surface of Earth. Right, then using the binomial expansion, we are getting the value of the gravitational acceleration at the height at g 1 minus 2h by r. The rest of the terms of the biology, see, if h is less than r, right? Then after this we are having the lots of terms according to the binomial expansion, right? But those terms will be quite less as compared to 0. Very not less as compared to, but it will be very nearer to 0. So in that case we can avoid these terms, right? And in physics also, whenever you are using the binomial expansion, the simple thing you have to do, you have to just multiply this factor in front, right? You have to just multiply the factor in front and the case is resolved, right? You have to just multiply the vector in front and this case is resolved. So we are having the second formula, G at height, it is 1 minus 2h by r. So whenever nothing is mentioned into the question, we have to use the general formula. When h is less than r, we have to use this formula, simple thing. So this is what the value of the G varies with respect to the height, right? So we are having two formulas, are simple. Say students used to get confused in this stuff, right? Okay, they always use this formula. Actually we have to use this one. But when condition is satisfied, h is less than r, we have to use this. How G with respect to the surface of the earth, it is varying with respect to depth. How G with respect to the surface of the earth, right, is varying with respect to depth. At surface we are having the value it as G capital M whole divided by r square, right? G capital M whole divided by r square. In this case I want to tell you all, right? In this case I want to tell you all that suppose if the particle is at this position, when it was at the surface, the gravitational force acting between earth and the particle, right? Okay, so the gravitational force was as because of entire earth when the particle is on the surface or in space. But when the particle is inside the, right, inside, and what happens? The gravitational acceleration, the force is acting as upon for this much part of the earth. So at that case, right, this G, okay, we are having the variation of the G as the, right, this side, variation of the G at the depth. We are having, this is a mass m dash of the earth and this is the whole mass of the earth, right, whole divided by, right, this is the radius of the earth and that is r dash square. Now as density of the earth is constant, right, density of the earth is constant, right? Now what we are going to see, density of the earth is got constant, so mass per unit volume of the earth, that is equal to m dash by v dash, that is density and that is constant, right? So in this case, if I'm talking about this r dash, can I say it is re minus d, right? Can I say it is re minus d? Yes, I can see that because this much is a d, the entire thing is r, right? This thing is r, this entire thing is r, right? And this much is d, so this part will be r minus d. So in this case, what will be the value of m dash? That is m into m into r dash cube whole divided by, right, r cube. Okay, and replacing the same here, the value of the G at the depth, right? Okay, we are getting it as a, okay, G m dash, it is G, what is the value of m dash? M r dash cube whole divided by r cube into r dash square. So this thing is going to cancel, right? So G at the depth, we are having G of m whole divided by, right, it's r cube, right? So it's r cube, okay, and this is r dash and that is re minus d. Further on resolving this thing, we are getting the gravitational, see, let us take G r square re minus d by r, right? So finally resolving this, we are getting GD as gravitational acceleration at the surface 1 minus d by r. This is the formula. We are not having any kind of the second formula for the depth, only one formula, right? Only one formula of depth, right? So we saw the three kind of the variation. There is another variation, right? How the value of the G is changing with respect to latitude, right? So for all of those cases, I'm giving you direct formula. The first one, right? For the height, we are having the two formulas. First, the general formula, that is equal to G at the surface 1 plus h by r whole to the power minus 2, right? If h is less than r, right, then we are having gravitational acceleration at the height surface 1 minus 2h by r, right? Second, at the depth, right, we are having the gravitational acceleration at the d, and that is surface 1 minus d by r. Second, the third case, as see, this is now as because of the latitude, as because of the, suppose this is the earth, whenever we are moving on from the right poles, sorry, whenever we are moving on from the right equator to poles, I'm sorry, this is from equator, right, and we are moving on to the poles, right, with respect to lambda. At equator lambda is 0, at poles lambda, that is equivalent to 90 degree. So for this, right, with respect to latitude, G minus omega square r cos square lambda, these are the variations of G, right? Okay, and in which omega is the angular velocity of earth or planet, angular velocity of earth or planet. Right, so these three important formulas are there. Now let's see that you can have a snap of it, right? I'm moving aside, and with this we have seen the densities also, but density more than that, that these things are important. Okay, now I'm moving aside, you can have a snap of it on the count of 5, 4, 3, 2, 1. In NEET 2017, right, one question was asked. The acceleration due to the gravity at height 1 kilometer above the Earth's surface is at depth d. This is the Earth's surface. From here, at the height 1 kilometer is the same at the depth d. Right? Okay. Now see, you can see this 1 kilometer. What is the radius of the Earth? The radius of the Earth is, right, 6400 kilometer. Now what actually the height, it is given 1 kilometer. Can I say h is less than r? Right? H is 1 by 6400th times less than r. Right? Okay. So in this case, at the height and the depth, right, the gravitational accelerations are same. So now here we have to consider, see, indirectly it is not given h is less than r, but we can see this, we can see this data, it is actually less than r. That's why we are using this formula, right? So it is gravitational acceleration at the surface 1 minus 2h by r, that is gravitational acceleration of the surface 1 minus d by r, right? Comparing this stuff, we are getting d is equal to 2h, so it will be 2 kilometer. So at the depth of 2 kilometer and at the height of 1 kilometer, we are having the same value of the gravitational acceleration, right? With respect to the surface at the depth of 2 kilometer and with respect to the surface at the height of the 1 kilometer, we are having the same value of the gravitational acceleration. C is the perfect answer. If mass of the sun were 10 times smaller and the gravitational constant were 10 times larger in magnitude, mass of sun were 10 times smaller, right? Mass of the sun is 10 times smaller and the value of the gravitational constant is 10 times larger in magnitude, right? Which of the following is not correct? See, in NEET 2018, this kind of question was asked, right, on the variation of G. Yes, it's important. What is the value of the gravitational acceleration? G is equal to, at the surface, if I'm talking about gm whole divided by r square. Right? If, see, if mass of the sun were 10 times smaller, see, we are having the raindrop will faster. Walking on the ground would become more difficult. Time period of the simple pendulum of the earth would decrease, and G on the earth will not get changed. So, very simple thing, right? Very simple thing it is, right? Mass is getting, see, mass of the sun, it is getting m by 10, and gravitational acceleration G dash is getting 10g. What will be the gravitational acceleration formula? It is G dash m whole divided by r square. So can I say gravitational acceleration? Right, I'm sorry, my mic. Hello, mic G. Hello. Oh, okay. Yes. So gravitational acceleration, that is equal to 10 g m whole divided by r square. See, so the gravitational acceleration G dash, that is equivalent to 10g. It is increased. Gravitational acceleration, it is increasing. It means that, suppose if I'm weighting 10 kg, right? Okay, my value of the G is getting increased. Mass is suppose 10 kg. What will be a weight? 100 Newton. If we are taking the value of the G as 10. Now, the value of the G is getting 10 times increased. So now suppose if mass is 10, then weight is 1000. In previous case, weight was 100. Now weight is 1000. Right? Now what will happen? Right? If weight is increased, obviously raindrops will fall faster, right? Because whatever the drop that is falling, it is a free fall, right? It is falling under the constant acceleration, and that value is increased, so it will, right, fall faster. Yes, obviously, A is the correct answer. Walking on the ground would be difficult. Yes, my weight is more. It is quite difficult to walk. Yes. Time period of a simple pendulum on the earth would decrease. Yes, T is directly proportional to under root of L by G. G will be high, T will be less. We have to select which is not correct. Yes, value on the earth, yes, will not get changed. See, value on the earth will get changed because here with the mass, the gravitational constant is also getting changed. That's why. Right? Let's move on to the next sum. A spherical planet has the mass m and diameter d. A particle of mass m falling freely near the surface will experience an acceleration due to gravity s. Right? See, acceleration due to this, see, this is r. It is g m whole divided by r square. So gravitational acceleration g m whole divided by d by 2 whole square. So it is equal to 4 g m whole divided by d square. This is the value of the gravitational acceleration. A is the perfect answer for this specific. Right? Imagine a new planet. Oh, wow. Equation of density is going to get come. Imagine a new planet having the same density as that of the Earth, but it is 3 times bigger than the Earth in size. It is 3 times bigger than the Earth in size. If the acceleration due to the gravity on the surface of the Earth is g, okay, then the surface. See, this is what the comparison between the planet and the Earth. See, equation of the g with respect to density, it was 4 by 3 pi rho g of r. Right? For a planet, let us take an example. This is for Earth. For a planet, it is equal to 4 by 3 rho g of planet. It is rho of planet g and r of planet. Yes, g is constant. Same density. Density is same, but it's 3 times bigger than the Earth in size. Right? And it's a very simple thing. If density is same, then g is directly proportional to r. Right? If density is same, then g is directly proportional to r. Right? I'm sorry, I need to adjust this mic. Density is same, then g is directly proportional 3 times that of the r. So can I say g of planet by g of Earth, that is radius of planet by radius of Earth, right? So g of planet that is equal to, what is the radius? 3 times the radius of Earth, right? Then this is gonna be G of Earth. So what is G of planet? This is 3 times G of Earth, right? D is a perfect answer. Simple. The density of the newly, this you all can do that. It's not a big deal. This is a homework from my side. You can answer all of this stuff right beneath the video, right? Okay. You can answer all of this stuff right, okay, beneath the video, okay. The height at which weight of the body will becomes 1/16th, right? Weight at what height will become 1/16th weight on the surface? NEET 2019 latest question. Weight at the height, G at the surface, 1 plus h whole divided by r, right, minus 2, that is equal to 1/16 weight at the surface, G, right? Okay, so this mg is gonna cancel, so we are getting 16, that is equal to 1 by h by r, right, whole square, 4, that is equal to 1 by h by r, right, and we are getting h value as equivalent to 3. So at the height 3r, right, okay, we are getting, right, our weight, okay, to be reduced by 1/16th, weight to reduced by 1/16th, okay. So this was all about the gravitational, right, the gravitational potential energy. Very simple thing, and a very simple classification I want to tell you all. Suppose this is an Earth, right? Before moving on to the concept of the gravitational potential energy, in short, right, I'm going to discuss the concept of the gravitational field. Around the Earth, there is a spatial area. Around Earth, there is a spatial area up to which the gravitational force of the Earth acts. That spatial area, it is known as gravitational field. One thing is also sure, this is not a fixed boundary. We can't say after moving 1 lakh kilometer away from Earth, we are out of its field. No. No, it's not like that. While moving away, far away from the Earth, the value of the gravitational force decreases like this way. The graph is like this way. It means value is getting, see, if you are moving 1 lakh kilometer away, 2 lakh kilometer, 10 lakh, 1 million kilometers away, right, 2 millions, 100 millions kilometer away, the value of the force is getting nearly equivalent to 0. The value of the gravitational field is getting nearly equivalent to 0. Right? Theoretically, we are defining the boundary around Earth, right, up to which the gravitational force of Earth acts. That is gravitational field. Simple terms. How gravitational field is going to help, right, in defining the stuff. Suppose Earth, infinite point, right, one test object of mass m is kept, right. One test object of mass is kept. There is one external agent, external space agency. We have given the task to external space agency, right? What kind of the task? This external space agency has to do the work such that to bring the object from an infinite position to any point under the gravitational field of the Earth by whatso path, right? We have given the complete liberty, freedom, whatever you want to do, right? I have given that this space agency, you have to bring the object from here to here, that's it.
Whatever you want to do, come on, move and do the task. Here comes the concept of the potential energy.
Now space agency will do, he will grab this object and is moving nearer to the point P, and nearer to the point P. Now he is also smart. Space agency is also smart. Safely he is moving. He is moving with the constant velocity. He is moving such that the kinetic energy of the particle is not getting changed.
He reached to the infinite position, grabbed that object, right? Okay, suppose he is NASA. He got a news at the infinite position. We are having the new mineral, right? Okay, new mineral is found, a new element is found. He immediately went to the infinite position. He grabbed that element. He took some samples. Now he's moving back. Now he's doing safely. There might be presence of some alien civilization. We have to keep that sample. We have to write that we have to keep this sample safe because we need to drop this down to the earth. So slowly, right? Being in the right, like he is completely in alert mode and he's moving. So he's moving in such a way that velocity of the particle is kept. The ex-alien civilization is having that type of the device, right, which can track the change in velocity of the particle. So this space agency is aware of. He's saying we have to move like a way that the velocity is constant so that alien civilization shouldn't get alerted and can attack on us. No. So he is doing the work against the gravitational field of the earth. This kind of the work is always stored in the form of the potential. See, work done in bringing an object, it is always stored into the form of the potential energy that is defined as the gravitational potential energy. In summarized form, whenever an external agent brings the mass from the infinite position to the point under the gravitational field such a way, if external work is doing, see, if external agent is doing work, then it always comes with the constant velocity. If earth is attracting, then velocity may get changed. Two different things. As of attraction it is coming, velocity may get changed. As of attraction, suppose earth is attracting, right, and we are रास्ते से जा रहा था, भेलपूरी खा रहा था, smell attracted me, so our velocity got changed, then velocity may get changed. But as of external agent, as of some velocity will not get changed. In both of the cases, work is done, right? And work is done either, see, whatever work is done either in support of the gravitational field or in opposing the gravitational field, it is always stored into the form of the potential energy. Work done is stored into the form of the potential energy, and specifically we can't define whether it is going against or in. Simple work done, right? Okay, simple work done that is stored into the form of the potential energy, right? Now that will define the concept of potential energy, right? Energy required to bring an object, test mass, from infinite to a point field of the earth. This energy, it is gravitational potential energy, and it is mass of earth, mass of object, whole divided by r. This is its formula. There are some noteworthy points related to this gravitational potential energy, right? What are those noteworthy points? Let's see this.
first. The value of the gravitational potential energy is always negative. What does the formula states? G capital M small m whole divided by R, where R is the distance between the test mass and the earth, right? Okay, suppose this is an earth of mass capital M, this is a small m, right? And they are separated by the distance R, right? Then this is the formula. So in this potential energy, the gravitational potential energy is always negative. The maximum value of the gravitational potential energy is 0. The maximum value of the gravitational potential energy is 0. It is always calculated with respect to the reference point. This thing we have already seen into the work energy and power, right? Okay, when we were dealing with the concept of the mgh, you remember that was like it was also gravitational potential energy, right? We were everything we were evaluating with respect to the reference point. Here also, right, the gravitational potential energy is always calculated, right, always calculated with respect to the reference point. In this case, in case of work energy or power, we were taking ground as a reference point. Here we are taking the infinite position as the reference point. At infinite position, right, the gravitational potential energy is 0. Right. So these are some noteworthy points related to the gravitational potential energy. Right. These are some noteworthy points related to the gravitational. Now this gravitational potential energy, if you want to take a snap of it, you can have it on the countdown of 5, 4, 3, 2, 1. Classification. It is defined for the masses and system of masses. It is also defined for the rigid bodies. Let's see this directly. Let's see this, right? Because this is the concept where we are going to solve the sums, and right after this, the work energy theorem is going to come, and we are going to see that also. Okay, see the work done to raise a mass m from the surface of the earth. This is the surface of the earth. From center of the earth, distance is calculated. See, work done to raise a mass. This statement says that work is done by external agency, right? So it means work is done such a way that velocity of the particle is getting constant. So it means that change in kinetic energy is 0, right? So whatever the work will be done, it will be changed into the negative potential energy. To raise a mass from surface of the earth, right, to raise a mass, here negative will be not there because the work is done against the field. Surface of the earth to height h. This is an initial position, right, and this is the final position, and this is also r. So what is the work done? That is change in potential energy, u final minus u initial. Final we are having position g m m whole divided by distance is always calculated with respect to the center. So final position is having 2r distance with respect to center. So it's negative of 2r, right, and minus, that is minus g m m whole divided by r. So the work done, that will be equivalent to g capital M small m whole divided by 2r, that is equivalent to mg r by 2. D is a perfect answer. Simple calculation. A body of mass m placed on the earth's surface, which is taken from the earth to the height of h 3r. Very simple. This is an earth surface, right? This is an earth surface, right? This is height r. A body is kept at the earth's surface, right? This is an initial position, right? From this it is brought, right, to the height 3r from the earth's surface. So this is a distance 3r and this is the final position. How much amount of the work is done? or you can say directly they have asked what is the change in the gravitational potential energy. That is same, work done by the external agent, right, in such a way that the velocity of the particle is kept constant. Right, so this will be the final, it is minus G capital M small m whole divided by 3r plus r 4r, right, plus G M capital M whole divided by r. So final it is 3G capital M small m whole divided by 4r, right. So this will be the change in potential energy of the particle. See, 3 by 4 mg, right. So these are the sums related to the gravitational potential, right, energy. Now let's move on to the most important concepts of work energy theorem, right. It reminds us about the chapter 6, right. It reminds us about the chapter 6, right. Apart from this, we can even calculate, right, about the gravitational potential energy also, right. Suppose I'm giving you some extraordinary sum. Four masses are kept on the vertices of the rise square. Or if you want to simplify this, right, okay, three masses, right, are kept. If you want to simplify this stuff, right, and understand this concept, three masses are kept on the vertices of the equilateral triangle of length L. How much work is needed? How much amount of the work done by the external agent is needed, right, to make the configuration like this way? Twelve. This is mass m. This is an initial configuration, right, and this is the final configuration. How much amount of the work is needed, right, by an external agent to convert this system, to transform this system from a equilateral triangle of length L to 2L. So what will be the work done by external agent? That will be change into the potential energy. So that will be U final minus U initial, right? It's a very simple thing. Final, right? See, if we are having, right, the system of masses, then we need to calculate the number of the pairs of the gravitational potential energy by this formula. Number of pairs of the gravitational potential energy by this formula. Number of pairs, right? Three particles are there, so it's 3 into 2 by 2. 3 pairs of the potential energy will be there, right? Like if I'm talking about the initial situation, right, and final, right, this is 1, this is 2, this is 3, right? So resultant potential energy of the system will be 1 with respect to 2, 1 with respect to 3, right, and U 2 with respect to 3. Suppose there are 4 particles, 4 into 3 by 2, right? 6 pairs will be there. 5 particles, from this we will get a number of pairs. Number of the pairs, we see 1, 2, 3. 3 pairs are having, na? So from this formula we can directly identify the number of pairs, right? So it will be negative of G capital M small m whole divided by L, negative of G capital M small m whole divided by L, negative of G capital M small m whole divided by L. So it's negative of 3G capital M small m whole divided by L. This is an initial potential energy. Final potential energy, again 3 objects, 3 pair, U12, U13, U23. So it will be final, it will be, this is initial. Final, it will be negative 3G capital M small m whole divided by 2L. So what will be the change in potential energy? Negative of 3G capital M small m whole divided by 2L, right, plus G capital M small m whole divided by L, right, 3. So 3G M capital M whole divided by L will get common, minus 1 minus half plus 1, right? So it will be 3 by 2G capital M small m whole divided by 2L. This will be the amount of the work done by the external agent. Okay, this is how also, this is for this system, right? Using this formula we can calculate the potential energies. In sixth chapter, now let's come back to this point. Change in kinetic energy. Work done by external, work done by conservative, work done by non-conservative, right? That will non-conservative forces, it means in kind of the dissipative or resistive forces like friction. In space, we are not having any kind of the friction. This will be 0. External agent, right, plus work done by conservative, that is equal to whenever the conservative force does the work, it is always negative of change of potential energy. So that is delta K plus delta U. This is an actually. Now, in our case, when external force, see why we took that formula into the previous case, that work done by external force is always equal to delta U. Why? Because W external, see, work is done in such a way that delta K is 0. That's why W external is equivalent to delta U. Right? W external, that is equivalent to delta U. Right? So in this case, we are not having any kind of the resistive forces or dissipative forces. And suppose if external agent is also 0, then total energy always remains constant. Whatever the variation we are getting, right, it will be equivalent to delta K plus delta U only. This is what work energy. This is the question solving approach. Only two equations we are going to use. The first equation we already used. If delta K is equivalent to 0, the work is done by the external agent, right? Okay, then it is always equivalent to delta U. It is always equivalent to delta U. Okay. This is only the question solving approaches. Analysis. Example. Let's take one example. Example of escape speed, right? Example of, right, the escape velocity or speed, whatever you want to say, right? It's a different concept, but we can understand it well by using the work energy theorem. It is one of the applications of the work energy theorem. Yes, it is explained. It is explained, right, into the different manner. Separately, it is explained, but it is one of the applications of the work energy theorem. Now, what does the analysis states? Let us take an example. Object is kept surface. How much velocity it is needed to reach at the height 2r above the surface of the earth? Velocity needed to reach at the height h is equal to 2r above the surface of the earth. Question is given. No presence, right? There is an absence of the dissipative forces, resistive forces. It means simply we have to use only one equation. Total energy at the initial position, total energy at the final position. That's it. Total energy at the initial position, total energy at the final position. At initial, it was at rest, right? Now suddenly, how much amount of the velocity is needed, right? So initial kinetic energy, the velocity needed is V. At this point with respect to center of the earth, what is the potential energy? Negative of G capital M small m whole divided by R. When it is reaching to the final point, the velocity is getting 0. So kinetic energy will be 0. At the final point, what will be the potential energy? Capital M small m whole divided by 3R. This m will get cancelled. Right. So it's V square by 2 is negative of G capital M 3R plus G capital M whole divided by R. Right. So V square by 2, that is equal to Gm. Right, it's 2gm by 3r. So velocity needed is 2 under root of gm by 3 of r. If you are projecting the particle, right, from the surface of the earth with the velocity v, with this value, then it is going to reach, right, up to the 2r height above the surface of the earth and it's going to stop. This is what the application of the conservation of energy is. Now suppose concept of escape speed, right? Concept of, right, escape speed. This is the surface of the earth, radius of the earth. A particle is released in such a way it can escape the gravitational field of the earth. Gone. Tata. Tata. Again, how much, with what velocity it should be projected? Okay, so that's an exact definition of the escape speed, right? The velocity, right, with which the particle, velocity with which particle is projected so that it can escape gravitational field of the earth. Again, work energy theorem. Dissipative forces are not there, so K initial, U initial, K final, U final. This is an initial point, right? Final is an infinity. So at initial point, right, what we are having? We are having initial kinetic energy as half mv square, initial potential energy as G capital M small m whole divided by R. At infinite, kinetic energy is 0. At infinite we are not, and beyond infinity we are not able to define, na? Right? What is beyond the earth gravitational field? Abba dabba chabba. So this will be the escape speed, that will be equivalent to 2g capital M whole divided by R. 2g capital M whole divided by R. Right? For earth, its value is nearly equivalent to 11.2 km per second. 11.2 km per second. One of the applications of the work energy theorem. Concept of interstellar speed beyond infinity. Let us take an example. This is Earth. We have to send rover to Mars, right? With what velocity v it is projected, right? Now see, let us consider this is an imaginary boundary up to which the gravitational force of, for us this is infinity. Beyond this, we have taken the values of the zero for escape speed, because we need to escape this gravitational field of the earth, right? Now if you are in a school, suddenly bell rings, how much amount of the velocity you are getting to escape from school? That's your escape velocity from school. Same, how much velocity this object is given, right? But when you are reaching beyond, right, when you are leaving the gates of the school, what will be your velocity? That will be the interstellar speed. The speed of the object in interstellar space. Speed of an object right? Work energy theorem. K initial, U initial, K final, U final. K initial, U initial, right? K final, U final, right? Initially it was at the surface of the earth, half mv square, right? Okay, this is minus G capital M whole divided by R. Beyond infinity, suppose it is crossing. So in interstellar space, this is an interstellar space. Beyond school, you are having the velocity. Now let's move on to the movie. Right, that thing. So in interstellar space, we are having half mv square final. Beyond infinity it is 0, right? So what is interstellar speed? That is equal to under root of v square minus 2 g capital M whole divided by r. Right, this is an interstellar speed. Sometimes this is also asked, right? This is also the one of the applications of the work energy theorem. This kind of the questions are also asked. Suppose this is a planet of mass m, this is a planet of mass 16m, right? They are separated by the distance of 10r. With what velocity this we should be projected such that it can reach to this planet? In this case also we are rapidly moving on to this. First of all, we need to find where net potential energy is 0, right? Okay, so in that case this will be your initial point and this will be your final. Just apply the work energy theorem. Initial kinetic energy, initial potential, final kinetic energy, final potential, right? One of the applications of work energy theorem. You will get the answer. With what velocity should the particle be projected so that its height becomes equal to the radius of Earth? Work energy theorem 2001. From surface initial position, it is released to the height final position r about the surface of the Earth. Simple calculation, right? Using the work energy theorem, right? K initial, U initial, K final, U final. That's it. Initial half mv square, potential energy g mm whole divided by r, final 0 g capital M whole divided by 2r, right? So this will be v square by 2, right? Okay, v square by 2, that is equivalent to, right, g capital M small m whole divided by, right, 2r. So v will be under root of g capital M by r. Sorry, m will get cancelled, right? M will get cancelled. First is, if with this velocity it is projected, it can reach up to the height height r above the surface of the Earth. Work energy theorem. The ratio of the escape velocity at the Earth to the escape velocity of the planet, whose radius and mean densities are twice. NEET phase 1 2016. Under root of 2gm whole divided by r, whose radius and mean densities are twice. Mean density of the planet is twice the density of Earth. Radius of the planet is twice the radius of the Earth. Consider this as equation number 1. Consider this as equation number 2. What will be the escape velocity of that planet? Under root of 2 g m dash whole divided by radius of the planet, right? Escape speed of the planet, it is under root of 2g. Mass is density into volume. Density of the planet 4 by 3 pi, right, rp cube, right, whole divided by rp. This rp is going to cancel. So escape velocity is under root of 2g into density of planet into 4 by 3 pi, right, rp square, right? So velocity of the planet, right, is directly proportional to, okay, density under root of rho rp square, right? So it's velocity of planet, velocity of Earth, that is equivalent to density of planet, radius of planet square whole divided by density of Earth and density of Earth square. Solving this, right, we are getting, right, what we need to calculate the ratio of so VE by VP, we are getting it as 1 by 2 root 2, right? Okay, you have to just replace the values. D will be the perfect answer. This is a question based on the escape velocity. Like this way, question based on the interstellar speed is also asked. One of the applications, right? Okay. Now, here it is one of the applications of work energy theorem. Why? Because this formula we already derived using work energy theorem, right?
So see, escape velocity is a kind of the special case application of work energy theorem, and it is that formula is derived separately. But suppose if that concept is not been taught, right, then first you need to apply work energy theorem here, then obtain the formula, and then move on to this evaluations and reach up to results. If mass m, particle of mass m is kept, Karnataka NEET 2013, height 3r from the surface of the earth, where r is the radius and m is the mass of earth, minimum speed, very nice question. Generally we are calculating the escape speed from the surface of the earth, but here a particle is, see, at the height 3r from the surface of the earth, this is the initial position of the particle. Now from here, with what velocity it should be projected so that it can escape the gravitational field of the earth? Very simple, work energy theorem, right? Very simple, work energy theorem. The initial point would be, right, this, and final point would be infinity. Okay, initial point would be this and final point would be infinity. So K initial, U initial, K final, U final. K initial half mv square, U initial g m whole divided by 4r. In interstellar space right now, see, if interstellar space concept has not been mentioned, right, till then beyond infinity we are not aware of any data. It means final results will be 0. If in question it is mentioned that you need to consider the interstellar space, the velocity of a particle in interstellar space, then and then your one factor will increase, one expression will increase. Just keep this thing in your mind. So this will be, m will get cancelled, right? So v square, that is equal to negative, okay, it is g capital M whole divided by 2r. Okay, so v will be, right, g capital M whole divided by 2r whole to the power half. With this velocity, if it is projected, right, with this velocity under root of gm by 2r, suppose if it is projected from the height 3r above the surface of the earth, then he can escape the gravitational field. The earth is assumed to be sphere of radius r. Okay, this you can do. Again, it's a question of the escape velocity asked in 2006. So this is a homework from my side, guys. You can answer this question beneath the a charged particle from infinite position to the point under the gravitational field is, the energy needed for that is potential energy. But I didn't told you about how much amount, how much number of masses I am bringing from infinite point. Earth, infinite, test mass m. Work done in bringing a point mass, a single point mass from infinite position to a point under gravitational field of the earth. In bringing a single test mass, not n number. See, potential energy, we have seen the cases of the n masses. No, here only one mass we are talking about. If we are having the system, we can evaluate that stuff, but your work is done, right, by an external agency to bring that single mass. So here that work done, it is equal to change in potential energy per unit charge, right? Okay, not work done, the change in potential energy per unit charge, that is gravitational potential, and it is defined as G capital M, not per unit charge, it is per unit mass, right? It reminds us about the electrostatics. So GMM,
right? Gm whole divided by r. This is the formula of the gravitational potential. Same it is applicable. The value of the gravitational potential is negative, maximum is 0. At infinite, the value is 0. Same. There is only one difference. There is only, right, one difference. So the same point we are going to see and write into the technical terms, right? Work done in bringing unit mass from infinite position to point under gravitational field. Of Earth. Right. Now, gravitational potential, it's a very simple term, right? Sometimes, see, same like gravitational potential energy, we can define it for the system of masses, right? And we can define it. See, gravitational field we already have seen. Now we need to see the relation between the field and potential. And before that, suppose if we are having the n number of masses, suppose this is mass m1, this is mass m2, right? And suppose we are having the n number of masses situated at the distance, right? Then with say n number of the masses, n number of the potentials with respect to the infinite. N number of masses, n number of the potentials, right? For the rigid bodies, right? This kind of the calculations, right, are there. It's a very simple data, right? We are not okay. Gravitational field we all are aware of, right? The spatial area up to which there is a force of a gravitational the spatial area up to which the gravitational force of the earth acts, right? Okay, so that is force per unit mass. So it will be defined as Jm whole divided by r square, right? This is a gravitational field. It is a vector quantity. Okay, it is a vector quantity. That is the relation between the field and the potential, right? Okay, so that is defined as I is equal to negative of del V by del R, right? This is the relation between this you all are aware of relation between the gravitational field and potential. This kind of the questions are asked in examination, right? I'm going to show you all in front. Okay, suppose let us take an example, right? If the potential is defined as, suppose electric field, the gravitational field is defined as, right, x square of I plus y square of j plus z of k, right? Okay, or if you want to define into the very simple terms, right, then we can define it as 3x 2y plus z of k. This is the equation of an gravitational field. Now in this case we need to calculate the potential, right? See, first of all I want to tell you all the potential terms never exist. There is always a potential difference. If I am saying the potential at a point, it means it is also with respect to infinity, right? Actually it is gravitational potential difference. Potential word, right, it is not appropriate because everything is with respect to infinity, right? Now suppose if we need to calculate del V, that is equal to, right, I dot del R, right? I dot del R. Okay, now we need to calculate the potential between the points, right, 0, 0, 0 to the point, right, 1, 1, 1, right? Now let's solve this using the relation between the potential and the potential energies, right? We are going to solve this stuff. Okay, relation between the potential and the potential energies. Okay, now integrating on both sides, we are getting I, right, dot dr. Can I replace dr as del x of I? Okay, can we write this simply, right? Integrating the things on both sides, integrating the expression on both sides, right? We are getting V, that is equal to integration of I dot del x of I plus del y of j plus del z of k, right? Okay. Now replacing the value of I here, this is from 0, 0, 0 to 1, 1, 1. Right. Now replacing the point, we are here getting 3x del x from 0 to 1 plus 2y del y from 0 to 1 plus del z, right, from 0 to 1, right. So finally, right, integrating this stuff, we are getting the potential difference, right, as 3x square by 2 plus 2y square by 2 plus z, limiting from 0 to 1. So v is equal to 3 by 2 plus 2 by 2 plus 2. So v is equal to 5 by 2 plus 2. 5. Potential difference is 9 by 2. Right? Okay, joule per kg. Okay. This is how things are asked. Okay, the relation between the potential and the potential energy. This is what all about is. Right? So let's have the glimpse of the potential, right? One another sum we are going to see, right? Okay, circuit. Okay, no, it's okay. One infinite GP sum we are going to see. That's very nice. Okay, here it is. Come on, man. Where it is? Okay, here it is. Right? Infinite number of the bodies are kept. Infinite number of the bodies are kept. Suppose each of 2 kg. This is 2 kg. This is 2 kg. This is 2 kg. Right? And this is 2 kg. They are kept at a distance, right? 2 meter, 4 meter, like this way. Sorry, 1 meter, 2 meter, 4 meter, and it extends up to infinity. We need to calculate. See, as I said, gravitational potential for the system of masses. Gravitational potential for the system of masses, right? So this is a case of infinite GP. When I'm going to calculate the potential, then it is negative of G capital M small m whole divided by 1. Negative of G capital M small m whole sorry. Not potential energy, it's potential, right? Negative of G capital M by 1, negative of G capital M by 2, negative of G capital M by 4, negative of G capital M by 8, it extends up to infinity. So you can see, right, infinite GP is formed negative of GM, right, I'm moving on. It's 1 plus 1 by 2 plus 1 by 4 plus 1 by 8, it extends up to infinity, right? So this is the case of infinite geometric progression. Right, for this kind of the sums, right, we are having, for this kind of the series, we are having the solution as, right, a by 1 minus r, where a is the first term, right, and r is the common ratio. A is the first term and r is the common ratio, right? A is the first term and r will be the common ratio. So what will be the common ratio if you identify the series is GM. The first term is 1, common ratio is 1 by 2. Now mass is 2. So what will be the net potential? Negative of 4G. Right? This is the perfect answer for this specific question. Two masses of M and 4M, they are kept and they are separated by distance R. From what distance, right? Okay. The net potential is 0. Suppose it is in distance x and this is r minus x. At this net potential is 0, it means G capital M whole divided by x is equal to G, right, 4M whole divided by r minus x. So this is going to cancel, G is going to cancel, r minus x, that is equal to 4x. Right, x is equal to r by 5. At the distance of r by 5, the potential, the net potential is getting 0. Right. So this kind of extra terms related to the gravitational potentials are also asked. It's a very simple thing. Right. Kepler introduced, see, Galileo, right, gave one statement and he was charged for blasphemy at that time. See, in that century, church was like, I'm sorry, extremely sorry about that. In that century, some expert was, right, dominating. Extremely sorry for that.
Okay, in that century, okay, I want to tell you all that very simple thing. Okay, Galileo was charged for blasphemy for giving a statement, right, about the actual position of the planets into the solar system and the sun, around the sun, right, and lots of statement is given for that, right. It was against some expert and he was charged for that. So in that case, I want to tell you all, right, Kepler was a person who gave them actually 3 laws, right, and who actually defined the things well, right. Okay, so those laws of the Kepler, right. See, this is what the latest thing is going on. The yellow dot is sun. Whatever the planets are there, they are revolving around this sun. Sun is also revolving around the center of the Milky Way, right. So actually, whatever the Earth it is revolving, it is not an circular path, right. As sun is also revolving around the right in the center of the Milky Way, Earth is also moving with that. So path is not exactly that, it's helical, but we are not able to identify that path because that point with respect to which sun is moving, it is billions of kilometers away from the Earth, billions and trillions kilometers from there, that we are, that value even we are not able to, if we have to define that into the light, millions of and billions of light years, right, light years, yes, that's perfect. So basically there are 3 laws of the Kepler's. The first, Kepler's first law, it is also known as laws of orbits. Second law of motion, that is laws of areas. And the third law, the Kepler's third law, that is laws of periods. This is the third law, right? This is the second law, the Kepler's second law of motion, and this is the Kepler's first law. Now what does the first law states? What does the Kepler's first law states? It states that, right, the Earth is revolving around the sun, not into the circular path, but into an elliptical one, and sun is at the one of the foci points, right. Earth revolves around sun, right, on elliptical path, and sun is at one of foci points, focus. This is what the Kepler's first law of motion states. Second, aerial velocity of Earth is constant. Now what does it state? It states equal areas swept in equal time intervals. Path is elliptical, it doesn't mean, right, things are getting changed, right. In the morning the span is of 1 hour, in the evening also the span is of 1 hour. On 1st January the span is of 1 hour, 1 hour is equivalent to 60 minutes, right, and the end of the December also, or in the November also, right, the 1 hour is equivalent to 60 minutes only, right. So in that case, right, suppose this is the thing, if this much area A1, right, this is an area A1, it is taking, right, to cross swipe this area in time T1, and suppose if this much amount of the area it is taking into the time T1, right, then this aerial velocity is constant, right, that A1 by T1, that is equivalent to A2 by T2. This aerial velocity is completely constant, right. This is not an exactly thing, right, what we are writing. Okay, A1 by A2 we can't write like this way, but we can say aerial velocity is constant, right. Aerial velocity, in another sense, aerial velocity we can write it as L by 2m, angular momentum by twice of the mass, that is equal to constant. What does the third law states? Third law states that the time period, the square of the time period of the revolution of a astronomical object around a point or a planet or a star is directly proportional to the cube of the radius. Removing this proportionality sign, we are getting t square is equal to 4 pi square by gm into r cube. This is what the, so this is the first law. What it states: Earth revolves around the sun onto the elliptical path and sun is at the foci points. Second, aerial velocity is constant. Third, law of the periods, that the time period of the revolution is directly proportional to the radius of the path, the cube of the radius of the path, the square of the time period to cube of the radius of the path. Okay, in NEET 2018, there are some PYQs related to the Kepler's law. Even, right, we are going to see this stuff. The kinetic energies of the planet in an elliptical orbit. See, there are the 3 points A, B, C. At the 3 points, we are having the 3 values of the kinetic energy, Ka, Kb, Kc. AC is a major axis, SB is perpendicular to the AC at the position of the sun as shown into the figure. Then, if I am going to tell you about the kinetic energy, right, see, L by 2m is constant. According to the Kepler's second law, L by 2m, that is completely constant, right? So in this case, can I say the kinetic energy is defined as L square by 2I? Well, R is the angular momentum of the system, I is moment of inertia. L is the angular momentum of the system and I is moment of inertia. Can I say IC is greater than IB is greater than IA? Right? Where I is moment of inertia. So if this happens, then according to this equation, if I is less, Ka is greater than Kb is greater than Kc. This is the correct relation of the kinetic energy. B is the perfect answer for this specific question. B is the perfect answer for this specific. A planet moving along the elliptical orbit is closest to the sun at the distance r1 and farthest at the distance r. Closest distance is r1, farthest distance is r2. Equal area, aerial velocity is constant of 1, that is aerial velocity, right, of 2. In another sense, L by 2m, m1 v1 r1, that is equivalent to m2 v2 r2. So v1 by v2, that is equivalent to what? That is r2 by r1. Ouch. This is the perfect answer for this specific question based on the Kepler's law. The period of the revolution of the planet is around the sun is 8 times that of the B. Time period of the revolution of A, 8 times that of the B. The distance of A from the sun is how many times? RA is how many times, right, of RB. Using Kepler's third law, T square is directly proportional to R cube, right? T1 by T2, right, whole to the power 2 by 3, that is equal to RA by RB, right? It means RA by RB, time period of first is 8 times the time period of B, so it is 8 times 2 by 3, right? Okay, so here we are getting it as RA by RB, that is equivalent to 2 to the power cube into 2 by 3, right? So RA by RB, that is equal to 4. Right? 4 times. The fourth is the perfect answer for this specific question. So this kind of the sums are there. A very simple explanation of the Kepler's law. So students, this was all about the gravitation. Right guys? So I must say, I will be waiting for all of your comments beneath the video. The maximum amount of the explanation, right? Yes, some of the students might be thinking there would be the less number of the sums. It's okay. Don't get worried. The practical sheet is also giving. And we are going to plan, we are about to plan the new awesome thing that is going to come in front soon on this channel. So guys, stay tuned, right? Lots of practice also we are going to do. Don't get worried. Okay, just move on with the flow and be with us on the, and stay tuned, on the PW English channel. So guys, this is Indrajit Singh, right, signing off from the desk. Bye bye, Sat Sri Akal and Namaste from my side, Bachaji. Bye everyone. Stay at home, stay safe, stay healthy amidst this pandemic. Again, we are going to come back with the solids, right? So bye everyone, stay safe.